You're using copy and paste. No colon or any command range. Right? So if you're in insertion mode, hit Control O, and then type in YY. You get Y number. That copy. If you want visual select, hit V and you can select visual.
Alrighty. Are there any questions? Any questions about the homework assignment?
Any questions?
Any questions?
Where do I begin?
Any questions? No questions? Then we're going to move on to the practice exam.
Sounds fun.
Yeah. Yeah, let's do that.
Okay, there are a few practice exams. There is the final exam for practice, and there's also the practice final exam. They're both practice exams. We'll start with this one. This is actually this was the actual exam from last year. And the preview is really simple. Download this file, unzip it, and everything is inside the folder. So I'm going to do the homework assignment.
Are we bringing our computer for this one?
No, because our exam is going to be different. I'm just using this one, but it does cover the same scope.
Is it Scantron, like you said, or?
No, well, I haven't decided yet.
Let's look at one that day. I don't mind Scantron. Then you'll know what your grade is.
You never know.
All right, so I'll unzip it to today's folder. All right. So this was the exam from last year, because the class was taking the exam over at the lab. Because back then they still close at 9:45, and these days they close at what 9:15 or sometime before that. So we can't really take the exam at the lab anymore. And that's why the format of the exam has to be changed. But this was from last year, and obviously you have to read the README file, which is just plain text. Each question has exactly one subroutine written in C to be translated into assembly language. In other words, it was a practical exam last year. This year will be different because I cannot expect you guys to be able to write the program and test it. I was grading based on the behavior of the programs, and this year obviously we cannot do the same thing. So we'll go ahead and just go to each question and take a look at the question. Okay. So we'll go ahead and take a look at V question number 1. So this one is Fibonacci.
Very fancy.
So we'll go ahead and take a look at main.c. And this was the subroutine that we have to implement. Any questions about this one? Compared to our homework assignment, this one is easy. Do you guys want to kind of go over this one and see how it's implemented? Sure?
Yeah.
No, we don't want to waste our time. This is good? Okay.
When we get done with this, are we going home?
Sorry?
I said when we get done with this, are we going home? Or are we filling in the rest of the hour? That's my question.
Today?
Yeah.
Well, we have 6 questions. This is first of 6.
This is all we're doing?
This is all we're doing, unless you guys have any specific questions. Well, but I just wasted $1.50 on Mountain Dew.
Yeah.
We cannot,
Hey, it's never a waste.
Yeah.
All right, so we're going to implement this in assembly. All right. So is there anything here that is kind of tricky that we cannot implement in assembly? Okay, let's take a look at the subroutine. It only has one single parameter, so that makes it kind of easy because even the order of parameters is not important here. Has no local variables, so that means we don't even have to remember to allocate for the local variable space. Comparing to a constant is easy because you can use the immediate mode for the 0. Comparing to 1 is also easy. And the only part that is a little bit trickier would be this part here. But then you just have to do it one step at a time. Push x on the stack, subtract it by 1, and then call Fibonacci. When Fibonacci returns, what is the return value? Where is the return value when this call returns? It's in EAX. We push it on the stack just so that we save it first. Do the same thing with this one, except you have to subtract 2 after you push x on the stack, or you can put x into a register, subtract 2, and then push it on the stack. Call Fibonacci again, and then EAX will once again have the result. Then you have to add this thing which is on the stack to this thing which is in your EAX. I would just I would pop whatever is on the stack into EDX, add EDX to EAX, then the answer is already in EAX, and that's it. That's how you implement Fibonacci. Any questions about the general approach? Any particular question about this one that makes it tricky?
Return 1.
You guys might have covered this, but don't quite remember if the countif def.
That will okay. That part is really just here so that I can use conditional compilation, so that I can use one rule to compile for an executable that uses the C code, and I can use -D as an option to GCC, so that the other one would use the assembly implementation. So that way I don't have to do any hand modification.
I figured it was going to be like 0 and 1. That's wrong.
So when you look at the make file, I have 2 executables. One is called main, and the other one is main C. The one of the main C one is going to be using the C implementation. The one that is main uses the assembly implementation. So this way, you can say make main C, and then you get the C version. So you can use GDB to see how it works. But when it is time to implement your own, then you just say make main, and then that will make the assembly version. So it makes your job easier. Okay. Yep.
So for that question, would you have accepted one line that said pound define CM in your Fibonacci.ns file?
No. But the assembly version is actually fairly simple too. Okay, so let's go ahead and do it anyway. Let's see how.
I wish you would tack accept that, please.
And I'm going to use Fibonacci.s. In other words, even the file is prepared. So this way, you can just go ahead and implement the subroutine. You don't have to worry about file management in this case. Okay. So over here we have Fibonacci already implemented. So the first thing I would do is to wrap it around using push EBP, move L, ESP to EBP, and then to close it, I'm going to use move L, EBP to ESP, pop L, EBP. So just usual standard stuff. Personally, I would also use return address 0. Oops, that's wrong because that's a old EBP plus 4.
Yeah.
Old EBP is 0. And then we have our parameter next to it, which is x. X is return address plus 4. It's not bad to keep writing this because it's just reinforcement to make sure that we remember when we are here, after move ESP to EBP, EBP points to its own saved value. And then above that is the return address because the call instruction was executed before the push L instruction. And then the parameter x is even above that one because it was pushed before the call instruction. So it's really helpful, I think, to keep that in mind, that the order of those things being pushed on the stack. All right, so once we have this part done, we can go ahead and implement the subroutine. The subroutine has to compare x to 0, and we can do this one relatively easy because we don't. Only one of the operand is a memory operand, the other one is a constant, which means $0 or the immediate mode operand works really well in this case, which makes it easier. And to use our usual convention, we basically say, if it is not the same as 0, we'll jump around the branch. So this one, we go to the first label, which is else if. The way I usually write my program is if I have a conditional or unconditional branch using a label, I would automatically define the label at quote-unquote the right place. So this way I don't have to later on figure out, okay, where am I supposed to put that label? Also, I would also use a jump here to go to end if, because I know that this is a conditional statement. Once you execute one particular branch, you have to get all the way to the end of the conditional statement. So I automatically put in these particular instructions because of the structure of the conditional statement. Any questions about this part? Now you don't have to write code, quite this much, in your exam because you won't have access to a computer. So I cannot, fairly ask you to write, programs like this. However, you will see my implementation, probably intentionally faulty implementation of something. So you still have to understand and read code during the exam. So just understanding the structure of, a conditional statement, will be helpful. Okay, so now I just have to implement this part here, which is return 0. Well, that's pretty easy. One instruction, how do we say return 0? Assuming that we go all the way to the end, there's one common exit point. Yep.
The movable $0 to EAX.
Yep, that's it.
Dang.
Yeah. Next one, same thing, except this time we compare to 1. But we are comparing the same parameter, in this case, which is x. And if it is not the same as 1, we also jump around that. But this time we have to jump to the label called else. And once again, we put the label else here. And then we also have to remember to jump all the way to the end of the conditional statement here before we insert the code to actually implement the body of the branch here. This time we want to return a value of 1. If we know how to return a value of 0, returning a value of 1 is pretty much the same thing. So these two branches are basically, quote-unquote, trivial branches. The only branch that is a little bit more difficult is the last branch here. If you look at it, it looks kind of complicated. You just have to do it one step at a time. Okay? One step at a time means, okay, I know we are not ready to do the return yet because we have to compute the Fibonacci of x minus 1. Well, let's go ahead and do that part first. In other words, we are trying to push x minus 1 on the stack. What you do not want to do is something like that. This is not a good idea. Why is it not a good idea? Because the intention is not to change parameter x and decrease it by 1. The intention is to push x minus 1 on the stack. So this would not be a good idea. There are several ways to do this. The most straightforward way to do this is to copy x to a register first, subtract 1 from the register, and then push it on the stack. This works. Okay? And then you call Fibonacci. Call Fibonacci. When Fibonacci returns, technically speaking, we have to add 4 to the stack pointer because the parameter which was pushed on the stack is no longer useful anymore at this point. Okay, so technically speaking, it is best to deallocate those 4 bytes from the stack so the stack stays balanced. Okay. You can reuse it if you want to, but if you plan to reuse it, you have to be very careful because we have to save the result from the first call to Fibonacci as well. The best place to save it is also on the stack. So what I would do at this point is to push EAX on the stack, and I will leave myself a comment here and say, save the result of the first call on the stack. So later on, I can reuse this result later on. Now I'm ready for the second call. The second call is the same thing. If I want to be lazy, I will just go.
Oh, yeah.
Don't do it.
Remember what happened last time?
What?
Oh, no.
Copy and paste? You guys don't trust me, huh?
It's only a couple lines.
All right, we'll just do it by hand then.
There you go.
Okay, and this time I'll just do it a little bit differently.
Don't you
same thing.
Yeah,
Hmm?
-2. You almost did it again.
How's that? Better? And then we can push it on the stack. And this is also kind of boring, so we'll do it differently.
All right, no need to show off. We're
Well,
doing good.
not to show off, but you guys have to know that these will do exactly the same thing. Okay, I'm not doing this to show off. I don't need to do that.
No,
Okay,
you
there's
are.
no need for me to do that. But you do have to understand the effect of these statements are basically the same. I don't need to push at the end anymore. Okay? But it will accomplish the same thing because what we are pushing here is the parameter itself on the stack. In other words, after, let me turn on the line numbers. After line 25, I would have the value of parameter x on the stack. And what line 26 is doing is adding this bit pattern to whatever I just pushed on the stack. I just pushed x on the stack, so now I know I'm just adding this constant to x on the stack. But what this is the 2's complement representation of -2. Now, how do we know this is the negative? This is -2 in 2's complement using 32 bits.
All F's are
Is -1.
Yeah.
So the next one down is -2. Very good. So that means just by switching the instruction from the first set of instruction to the second set, I'm showing you how to use the stack or alternative ways to use the stack, as well as the implementation, the use of 2's complement of -2. Yep.
The second way would be much slower than the first way, right?
The second way is actually slower, yes, because you're accessing memory more often than the first way. Correct. It also depends on the cisc instruction set and also cisc addressing mode that are probably missing in most RISC architectures. But they can get the same job done, because it's still the same type of operation. We still accomplish the same thing using the second set of instructions. All right, so now that we are done with pushing the parameter on the stack, we can call Fibonacci in, Fibonacci. And when it returns, it is still a good idea to add 4 to the stack pointer. Even though if you do not add 4 to the stack pointer, nothing bad is going to happen here, except for the waste of a few bytes on the stack. Because even though the stack is going to be imbalanced at the end, this instruction will make everything balanced again. Okay? Any questions at this point? We're not quite done yet, because when we are at this point, EAX has the result from the second call to Fibonacci. So that means it is time to pop the result from the first call to Fibonacci. And the easiest way to do it is to pop it into a register that we do not need to save, and also not EAX itself. So after this, we can then add L, EDX to EAX. This time it is important to remember which one stores the result. Okay, because we know that we're adding these to registers. The question is, where are we storing the result? The second operand is always the destination. And after that, there's nothing else to do. We are already at the end-if label. If you want to, say jump to end-if. There's nothing wrong with it, except it is redundant, because we are already at that point. So typically, I just don't use the jump instruction at that point, and that should do it. That's
I
the
have
end.
a question.
Yep.
You were saying we don't need to add 4, but then your pop L EDX, wouldn't that make a difference if you didn't add 4 to the stack pointer?
And it's a good question. The question is, okay, I'm trying to, I want to make it so that I can have 2 different sets and alternative. Okay, so if not tricky. If not tricky, we'll do it this way. Else, if it is tricky, we'll do it the other way. Okay, this other way to do things is basically, because we know that we have 4 bytes in between where the stack pointer is pointing at and the thing that we actually want to access.
Yeah.
So what we can do is to say add L, and in this case we will put an offset of 4 ESP to EAX. Yep, that will do it. And that's it. We don't need to clean up because if we don't clean up, the stack will still be balanced. In other words, this code will work even though it's wasting space
So
on the stack.
ESP+4, that dereferences and it puts that into EAX.
What this does is we are almost going to where the stack point is pointing at, but
But
not
you're adding
exactly.
4.
We're adding 4, which
And
means
you're
we're
putting that
not.
into EAX,
Exactly.
Which is exactly what you did above.
Right, but if I still want to balance the stack, I should do this.
Okay.
So these two alternatives will do exactly the same thing. It's just that one involves more instructions, and the second one is involves fewer instructions, and it's a little bit more tricky to look at. Yep.
Doesn't EDX hold the return value, but most 4 bytes, most significant 4 bytes?
But the type of the return value is only 32-bit, so the most significant 32 bits or EDX is ignored. So in this case, only EAX represents the return value, so EDX can be changed.
How do you know one is ignored and one is not in assembly?
In assembly, you don't, so you have to refer to the C code to see. You basically have to make assumptions because we are using a 32-bit machine, so int itself is a 32-bit integer. That's a good question. Yep.
So we're using the two's complement on line 26 because it's an unsigned notation, or why are we doing that?
So much harder.
This is -2 because I have to subtract 2 from x.
And it's just the, and it's the two's complement of 2.
It's the 2's complement in 2's complement representation of -2. In other words, if you apply 2's complement to this bit pattern, you get 2 back.
Okay, and we're doing that because it's an unsigned.
We are doing this because I want to show you what are the alternative ways to represent -2.
Okay, would you be able to do the same thing just by subtracting 2 from?
Yes. Yep. So they will all accomplish the same thing, but I'm using different ways to implement this program just so that you can see the different ways of implementing the same thing. Any questions at this point about this program? Yep.
Isn't line 34 meaningless since we're going to be balancing the stack again with the...
Line 34 is it's not exactly meaningless because with this here, depending on how much you want to do the computation, this will make sure that we don't waste 8 additional bytes on the stack each time we invoke Fibonacci. Without that, we'll be wasting 8 additional bytes on the stack, which means we'll run out of stack space sooner.
Well, not very soon.
Not very soon, because last time we tried to run out of stack space, it took a while.
Yeah.
Yep.
Why are we at 8 now?
We're adding 8 because there are 2 4-byte things on the stack. One is the saved value, or the saved result from the previous Fibonacci call, and then the other one is the parameter of this particular call to Fibonacci. Okay, any other questions? No other questions?
What do you use? Do you use the tricky when you're, like, let's say when you were working and doing your code? What would you prefer?
You know what we should use? You know what we should do on the test? Go pound if wrong. Put, like,
If
3
tired,
different ways.
if wrong, yeah. If frustrated. Yeah. The tricky one, if you look at the code, is actually one instruction shorter than the other one, and it runs a little bit faster. And the best part of the second version is it doesn't use up another register. The
Yeah.
first chunk of code uses up EDX, but the second one does not use up any additional registers.
Okay. What do the standards say? Let's get it right.
The first one's much faster.
The first one is?
Yes, if not tricky, that first block is fast. The second block.
Isn't using the pop also automatically using the memory?
I think it's about the same because the pop has 1 memory access. This only has 1 memory access too.
Yes, but popping is optimized to be faster than directly reading from the stack.
And within the second version, we can also have count if cisc else.
All right.
And
All right. I'm sorry. I'm sorry I brought this up.
Well, I think it's a good question, because now we can look at the risk implementation. Because everything up to this point depend on instruction sets or instructions, and also addressing mode that we have access to, because the i386 is a cisc architecture. What if you only have a RISC architecture and you don't have these fancy addressing modes or the fancy instructions like pop and push? Those are fancy instructions. So now you have to do everything using just add instructions and move instructions. Okay, so let's see how we can do it this time.
Let's just think about it for a minute. We'll just throw it out there.
It's too late. I got enough caffeine in my body already. So I'm already running in turbo.
All right, go ahead.
Yeah, it's already up to 18 psi. So.
See you bouncing up there?
Well, remember, I might have ADD, so caffeine actually calms me down and stops fidgeting. Okay. Okay, so let's go ahead and take a look at the RISC implementation of the same thing. Okay, what would you do, if this is the RISC implementation?
Okay.
In the RISC implementation, we don't have based addressing mode. We have indirect but not based. So in this case, what we will have to do is to copy the stack pointer to a unused register, say EAX. Then we have to add 4 to EAX so that we end up with the same effective address as the first operand of line 34. Once we have the effective address, then we can go ahead and use move indirect EAX to EAX. And if I want to balance the stack, then we can just do the last instruction as before. So that's the RISC implementation. But it does the same thing as this particular one. Okay. Now, I think it is important to see how all these alternatives will still end up doing exactly the same thing. Because I think the effect of these instructions on the stack is what is the most important part about this question. So you have to understand how all these different ways of implementing the same thing, even though they look completely different, they still end up doing exactly the same thing. And that's really important. I think that's one of the most important part of this assignment, or this question in this case. So are there any questions? No. Okay.
I have a question. Oh,
Yeah.
All right. No, go ahead. That's fine.
Don't bite your tongue.
Well,
Go ahead.
this is sort of homework related. So
Go ahead.
Are you guys okay with that?
I guess.
Okay, so let's go back to where old EBP is.
Okay.
We have to change this just a bit here. So let's say X, okay? X is, I don't know how I'm going to change this yet, but let's say X is a pointer to X.
Okay. X is a pointer to
The value of X. So let's say X is a pointer to X, which is an integer.
But that won't work in this case because we are only passing by value here. So we cannot change X to be passing by reference in this case.
Well, let's figure it out. Okay, so just, you can put your X back, and then let's just, here's what I really want to know. When I have a pointer and a double pointer, or not a pointer at all, okay? And then I have those labels up top. This is so confusing.
Not yet.
So we're adding, like you're saying, compare along $0x percent EBP, right?
Right
Which
here.
is the content of X, or the
Yes,
value
this is
of
the
X.
parameter.
Yes.
Yeah.
So how do we do that same instruction with, let's say, a pointer or a double pointer?
Are you comparing what the pointer points to, or
No.
are you comparing the pointer itself to null?
We're comparing the value of the content.
Then you have to dereference
Dereference
whatever
twice
X
or
has.
once. once or twice?
That part depends on whether it's a single asterisk and you're comparing what the pointer points to, or whether it's a double asterisk and you're comparing to whatever the pointer points to, the dereference of what the pointer points to.
I just want to get to the content. So
The content, but everything is content. You have to.
I know, but just bear with me, because I know you're thinking ones and zeros, and I'm just thinking artistically right now. So let's just humor me for a moment, okay?
Maybe another question can answer your question. I don't know.
No.
No, but I'm not kidding, because that would not be a good example to look at, in order.
Oh,
in
no, I
terms
see
of
what you mean,
Pointers.
yeah.
See,
Yeah,
this
yeah.
one has pointers.
Okay, this is what I was looking for. You
Okay.
found it.
All right, so.
Jack, you're the best.
Okay, so this one, we have. Okay, which subroutine do you want me to look at? Because we have the first subroutine printing a coordinate, where we pass a pointer to a structure in as our parameter, and we want to access two different members of what the pointer points to, or the structure that the pointer points to. We have a swap subroutine here. You pass in two pointers to integers, and then what we do is we dereference the pointer and store it into my local variable t, and then I dereference the other one, store it over here, and then the other one. I think this one is basically what we did in class. We have done swap already.
Yeah, that's okay.
That's okay?
For me.
What about transpose? Transpose, I think this one it can be interesting because it is taking
Yes.
the address of a member of a structure that is pointed to by a parameter. I challenge any C instructor to say that again.
Can you repeat that?
Go ahead.
No, can you repeat that? What you just said?
Oh, okay.
I can TiVo.
So that grabs
Yep.
it grabs what x and y are, and then it says take the address of.
Okay, I'll say it again.
I sound like an idiot, right?
No.
Okay, this
fair
is
enough.
taking the address of the member X of the structure pointed to by P coords. Okay, so you have to kind of keep a picture of what is this whole thing about. Okay, I cannot really draw the picture
Just do it on the
effectively.
whiteboard, we don't care.
I have to use the whiteboard
Yeah.
in this case. You guys all have smartphones, you can take a picture. All right. So we'll take okay, let's see what is on the stack and how everything is set up in this case when we have a subroutine calling transpose coord. There are two parameters here that are pushed on the stack. The way I draw the stack is higher addresses will be pointing up. Okay? So this would be the second parameter pushed, which is our we only have one. Okay. So this is our parameter P coord, which is a pointer to a struct coord. And then we have our usual stuff, which is our return address, takes up 4 bytes. By the time we get to the inside of the subroutine, we will also have ODBP here. Is that okay?
Yeah.
So by the time we get to this subroutine call, we have that stuff set up on the stack. And because we don't have any local variables, we'll have EBP and also ESP pointing at the same spot because we don't have the need to reserve any local variables. We reserve space for local variables. The question now is, what exactly is P coord? It takes up 4 bytes because it's a pointer. A pointer and integer, they all take up 4 bytes. So these 4 bytes is not what I really want to access. These 4 bytes will point to a struct coord. Okay. A struct coord, so this is a struct coord which takes up multiple bytes. And I'm going to have to look up the actual definition to find out how it is defined. We have struct.h. So when you look up struct.h, you know that there are 2 members. Assuming that there's no special things going on, we know member X is going to have the lower address, member Y is the one that has the higher address. Is that okay? So now we switch back to this code here. So the question is, what are we going to do in order to pass our parameter. This is the wrong spot. No, it is the right spot. So the question is, what am I going to push, or how do I push this on the stack? The address of member Y of the structure that is pointed to by P coord.
Okay.
Yep.
Y has the higher address.
Y is the one that has the higher address because it's the second member of the structure.
So what is that? Okay.
But that does not even matter to you because
Well.
the include file already defines the constants. It really doesn't matter because if you look at struct,
Is that the way? Are they pushed somehow? Is that what you're talking about?
sorry?
Are they pushed, and that's why it has a higher address?
No, because it has to do with the order of the members.
Okay.
The first member, which is X, has a lower address than the next member, which is Y.
So always the last address or the last member has the higher address.
But that part really should not matter because we should not be using 4 or 8 or constant,
I'm just
offsets.
preparing for your tricks on the final. I know they're coming.
Yeah.
It's really hard to have tricks because it is. Things can be tricky when you're teaching classes where things are not black and white. Assembly language programming is as black and white as it gets.
But remember that one question on the last exam where you said, "What is here?" and it was like something that was beyond what we knew. It was like something outside of the stack.
Yeah.
That was a trick. Anyway.
I would consider that a trick. It's fun.
Yeah, but you guys have all the extra credit for that test.
We appreciate that.
Okay, so the question is, what is the address? The question, when we look at that parameter, let me highlight the parameter first so we can focus on our task. So we want to push this on the stack. The question is, how do we specify that using assembly instructions? We start with EBP pointing to this location. We know that EBP plus 8 is going to be the 4 bytes that will serve as a pointer, but it points not to Y, but points to the beginning of the entire structure. But we also know that this offset here, the offset between the member Y and the beginning of the structure, we usually call that coord, in this case underscore Y. This is the name of the structure. That's the name of the member. Okay, that's the convention of this class. That we have been using. Okay. So what do we do?
So we have to reference
Okay. So what we'll do is we need a move. Okay. At this point, I can switch back to the text editor. Okay. So instead of, let's see. Could do that. Split. All right. So we'll do exactly the same thing. The first part is going to be boring. And then we have our P coord equals to return address plus 4. And then the other part is boring too, but it is important that we remember to do it. And don't forget the return instruction too, because in the test, I might just miss that one last instruction. But without that instruction, it does mess everything up. So you got to remember to check for the return instruction. Okay, so now getting into the body of the loop here. Okay. We have to push the address of member Y of what P coord points to. So we work on this, step by step. What is EAX at this point? I'll turn off the one bank of the light so the contrast is better.
Value.
It is the pointer itself, isn't it? Okay? Because we are putting the parameter, which is a pointer, into EAX. So we can say that EAX is P coord. It points to a struct coord. Is that okay so far? Does that make sense? Okay. So when you look at the picture, that EAX is now the same as P coord. So that means we have EAX at this point pointing to a P coord structure. Is that okay so far? So we are pretty close because EAX is the address of the beginning of the entire structure. We don't want the beginning of the entire structure. We want the beginning of member Y of the entire structure. Yep.
Would the next one be move chord underscore Y?
It has to do with chord underscore Y, but we don't use a move. Instead, we use add L. And also, remember to use the $sign because if without the $sign, we are using the offset as the location that we want to access, which is not what we want to do. So we will add this constant to EAX, and now we can just push EAX on the stack. Okay. Any questions about this one?
So that convention for like chord underscore Y, we can't just assume that on your test. We have to find that defined somewhere in this.
In the test, I will give you some given, so you can make assumptions and say, okay, if I use the name of the structure with an underscore and also, the name of a member of that structure, you can assume that label is defined to be the offset from the beginning of the structure to that member.
Okay.
You can almost count on that as a convention that I will give you. Mm-hmm. So you don't have to worry about the mechanism to make that happen. You just make the assumption that it is already defined correctly.
Let's do the tricky version now.
Okay, let's do the tricky version. The tricky version of this, we'll do it to X. There are really several ways to do this. Okay, we can push P coord EBP on the stack, and then we add long coord X to whatever the stack pointer points to. Okay, you guys know that part already, huh? Okay, and then we call swap int 32. When it returns, we have to remember to reclaim those 8 bytes in this case because we pushed 4. We push 4 bytes per parameter, and there are 2 parameters. So there are 8 bytes on the stack that I have to reclaim at this point. But we are not quite done yet because we are just done with the call to swap int 32. We have to remember there's a return instruction here as well. So you got to remember the last part, which is to move the parameter itself to EAX as our return value. Is that okay? Because this is our last thing to do in the subroutine. We have to return whatever the pointer is, we will use it as our return value. Are there any questions about the implementation of transpose coord? Questions? Yep, go ahead.
I actually have a question going back to Fibonacci, or actually here too, it's just an add a. So right after call, what is BST pointing to? Right after call, swap it to. Before you add a to it.
Okay, let me try to turn in the line numbers.
Line
so
18 and 16. Like right after line 16.
Right after line 16, the stack pointer will still be the same as if it is line 14. So it will still be pointing to the first parameter of the call. But the parameters, to me, as the caller, are useless at this point. So I don't need those items on the stack anymore, and that's why I can just add 8 to the stack pointer to deallocate those 8 bytes.
Okay. In the Fibonacci one, like after with the recursion, you called Fibonacci again, and then you added 4 to the stack pointer, and then you pushed a value onto EAX. But wasn't there already a return value at EAX?
No, EAX is the return value. Yes, it is. But I want to save the return value because the second time I call Fibonacci, the callee will want to use EAX to return the value as well. So if I don't save EAX at that point, EAX it will be overwritten by the second time I call Fibonacci, and it only stores the return value from the second call, and I would have lost the return value from the first call to Fibonacci. No, this is the first parameter, so we are only interested in x.
You just,
I pushed y already. This is going to push the address of y. That pushes the value of x.
you did the tricky version with the other brand.
Sort of tricky.
Can you explain number 20?
Number
Line
20?
Number 20. Because basically after
Okay, there was
call-
another hand. Let me answer his question first and then get back to
Can you
you.
explain line 14?
Line
14.
14. Okay. This one here?
Yeah.
Okay. What did I just push with this instruction?
That's the struct.
Push the address of a struct coord on the stack, right? And what am I adding to? Okay, what am I adding and what am I adding to?
It looks like the right side is the content of the struct.
Okay, hold on.
I don't
Okay.
know what the content is, because it has two things, so.
It's the offset from the beginning of the structure to the very
Right. So coord x is the offset from the beginning of a.
But usually when you want to access somewhere, you use the indirect thing.
Indirect thing? But
use
I don't
the-
want the value of member x of the struct coord. I want the address of member x in this case. Because when you look at the C code, it says it'll take the address of member x of the coord pointed to by p coord. And that's why I have to do it this way, because I am not interested in the value of that member. I'm only interested in the address of that member.
What is the indirect of BSP? Is that the address of x?
No, this is what I just pushed on the stack, because the stack pointer always points to the last item that you push on the stack. What I just pushed on the stack is the parameter p coord, which is a pointer to a struct coord.
Okay, then what is that doing? The C code? I'm not getting
In the
it.
C code,
Yeah.
this is the first parameter, and the way you read it, there are several ways to read it, but I would read it as the address of member x of whatever struct coord the p coord points to.
Okay, then I'm not getting how is it? No, how you're accessing the address x of the struct right there at line 14.
Because this is already pretty close. This is the beginning of the entire struct coord, right? Because we know that p coord is a pointer to a struct coord. So p coord is already pointing to the beginning or the base of a struct coord. I just have to add the displacement or the offset, if you will, of member x from the beginning of the entire struct coord.
Are you saying you don't understand where that coord underscore x is defined? Is that what you're saying?
Yeah.
Yeah, it's defined by another.
Yeah.
Okay, I think I kind of get it.
Okay.
You just gotta assume that that's already defined.
Yeah,
as
it's already
0.
defined, and it's coord underscore x is the offset from the beginning of a struct coord to member x of that structure.
So basically, in this case, it's 0.
Yeah, we're just assuming that. That's
Well, it it is 0 the way it is defined currently, but if I swap the order, it won't be 0.
Which you will probably do.
It doesn't matter, because that's why we like symbolic constants, because we don't really need to know the actual ordering of the members. We doing okay so far? Any other questions about this particular question?
Go over line 20.
Line 20? Okay, so I almost forgot you saw. Okay, line 20 is
Right now it's
line
21.
21? This specifies the return value.
Line 23.
It is. This is doing the same thing as that.
But what does the call returns? Does it return lines?
Hmm?
What does the call return?
The call returns whatever p coord is.
So
In other words, whatever the parameter is, I return exactly the same thing.
But then why do we need 21? Line 21?
21?
Because EAX should have the return stuff, right?
Hmm?
EAX should have. the
No,
return
EAX,
from
I do not know what EAX has. I don't know what EAX has because if you look at the C code of swap, it doesn't return a value. So I have no idea what is the value of EAX when swap returns. So that's why I have to make sure that EAX has P chord before I return from the subroutine. Yep.
I just want to bring this up really quickly because it was confusing me a bit. So L1, let's say, is a label that equals 4. If we use the $sign L1, that will give the address of where that label is, right? Or where L1
Okay,
is.
that's a good question. Yep, go ahead.
But with the .inc file, it's like defining, right? So it's saying wherever chord X is, turn it into this value, right? So $sign chord X is actually that value because it's not an address, it's the value.
Okay, let me see if I can clarify that.
It's a symbol, not a label.
Okay, so
Right.
so let me just do this part here. This is a simple label definition. What this line does, L1 equals 4. What the assembler is doing is to say, okay, wherever I see L1 as a symbol, it is the same as the constant 4. That's all it's saying. So what you're asking is, what is this doing as opposed to what is this doing? That's your question.
Yes.
So in this case, EAX ends up with a value of 4.
Right.
In this case, if it is successful, EAX ends up with the content at address 4.
Right. And then if you have L1 colon, if it's a label, in other words.
Okay, if it is a label, okay,
Then
when you
L-
use the colon, it is the same thing as equals dot, which is
Right.
whatever the address is for that particular segment of memory
So in
is
that
at this
case,
point.
move L1 is going to end up with the content at address, or the address.
Okay, in this case, if I put L1 colon here, this will end up as the address of this particular move L instruction.
Yes.
This will end up as the instruction itself, or the first 4 bytes of the instruction move $L1 to EAX.
Okay. I just wanted to bring that up.
Okay.
I don't know.
But
If
is that
that's-
okay?
I don't know if that helps. But
Did I answer the question now?
yes.
Okay, very good. Go ahead.
Can you explain the return P chord?
Return P chord. So you're talking about line 21 and verses. Okay. Line 21 here, and also we want to go to
Yes.
this particular line.
I want to make sure I understand exactly what's being returned. What is being returned?
In the C code,
And see, yeah, what's going to be in EAX?
That's the address of.
Is it the address of?
the address of the struct P chord, the struct chord that is passed to me as a parameter. It's the same thing.
Okay.
In other words, it's kind of like a pass-through because this way I can stack up, calls together, and not having to, separate the calls from, onto individual lines. Okay, when you look at transpose chord, the way I use transpose chord is like this. Do you see how this is how this is done? Test is a chord, and %test is the address of a struct chord. That's what we need to call transpose chord. But transpose chord returns just whatever it was passed to it. So that means print chord is actually getting the address of test as well. So that means I'm ready to print the structure test at that point. I don't have to separate this into different calls. I can stack up the calls like this.
Okay, so like it's just purely for condensing the code.
Yeah, more or less. But that's a lot of times C programs do this. They whatever pointer you give it, it also returns the same pointer. So it will act as a pass through, so that you can use the subroutine call inside as a parameter to another subroutine
The
call.
subroutine inside the subroutine, it still performs some other operation, right? That we need to do.
Sorry?
So transpose court is still performing some other operation you need to do though, right?
Yeah, it's doing operation to what the pointer points to, but it doesn't do anything to the pointer itself.
Okay.
Yes?
In the homework, there's a subroutine where you are using malloc in there. Did we go over anything like that last Thursday or at any time at all? Implementing malloc in assembly?
Malloc?
Yeah.
You just call malloc.
Okay.
Yep.
And you just like push to the right.
The size of is the only part that is a little bit tricky because you have to
Did we
use.
talk about that too? I remember that.
Yeah, we talked about that part. You know, in your print, or the day before that, or the lesson before that, because in your executable called print tree node offset, the last line should print the size of a struct tree node, and that's basically the size of. So in assembly, you just use that label as if it is the size of a struct tree node. Okay. Any other questions?
Next.
Next. All right. We are definitely getting a little faster now. Okay, another main, and this time it's a BST node. You know, it's a
Beast.
it's a nasty one. Okay, and this is the one that you have to implement. You know, last year, you know, people have to implement this particular subroutine, which has a lot of resemblance to your homework assignment.
Let's do it.
I cannot do it this way. I can implement specific, you know, ones like this one. How about this one? Just, you know, we'll focus on specific ones. we'll just pick the difficult ones. Okay, just pick up the difficult ones.
Do you need an admin to do?
Huh?
Do you need an admin to do?
No, I don't think I can handle another one.
Shouldn't underestimate yourself. Shouldn't underestimate yourself.
You can only use nitro so many times before you blow up the engine.
This is true.
All right, so we'll focus on one single line here, which is, you know, P node points to v.I. Okay. All right, so we'll focus on this line, but first of all, we want to look at, you know, struct.h just to see what is a BST node. Does that look familiar to you? Binary search tree, bin tree. Okay, so it's basically the same as a tree node. So in other words, you can look at, you know, this and say p less is a pointer to another BST node. But what is v? V is really quite simple. V is the value, and it's a structure, but the structure only has one single member at this point. It doesn't mean that it will stay this way, because I can always say, you know, something like this later on, which changes the displacement or the offset to I to a non-zero. So that means you cannot use, you know, always assume the offset from the beginning of a struct value to I is 0. Okay. So assuming that we make that, you know, this change, how are we going to implement this code? So we'll go ahead and implement the code in place here. Any ideas? We'll try to deal with the left-hand side first, okay? We'll compute the address of the left-hand side, because the right-hand side is really easy, so we'll leave it to later. We'll compute the address of the left-hand side. Okay. Okay, we'll start with P node. Let's go ahead and move P node, which is a parameter. If it is a parameter or a local variable, you typically want to use the base addressing mode with EBP, and we'll just move it to EAX. The question is, what is in EAX at this point?
Beginning
of a struct node? Okay, very good. So EAX points to a struct BST node. Okay. Next, we need to find the address of member V of a BST node. How do we do that? We just did it, you know, in the previous program.
Just
Add L. Okay, very good. So we have BST node underscore V, because that's the name of this member, to EAX. So now EAX points to member V of a struct BST node.
We're almost there.
Almost there. Okay, but exactly what is a V? What is member V? Member V is a struct value, and I is a member of a struct value. So what you can do is just to add value underscore I to EAX. So at this point, EAX points to member I of a struct value that is member V of a struct Bst node that is pointed to by E node.
Can you draw a picture?
Yep.
So this is like a struct inside of a struct?
It is, yes, it is a struct. It's a, okay, V is a member of a structure, but itself is also a struct. And so I is a member of a struct, which itself is a member of another struct. Yeah, so we have nested structure in this case. Is that okay?
Yep.
In terms of concepts? So in this particular case, I could have optimized the code and add both constants here. Because if you think about it, these two add-Ls can be combined into one because each one is only adding a constant to EAX. So I can just pre-add the constants and use only one add-L instruction instead of two. Yep.
How would you do that?
Just the plus.
Just say plus value underscore I. But that would make it harder to explain because I cannot explain it step by step. Separating it into two instructions makes it easier to explain it.
Did you need the dollar value underscore I or just value? You wrote value underscore I, but it's supposed to be dollar value underscore I.
It is dollar because otherwise we'll be going to a really low address to grab its content.
Okay.
The dollar symbol or immediate mode
Well,
means whatever.
When you just rewrote it, you wrote it without the dollar. So
Dollar applies to the whole expression.
the whole, okay.
Yeah,
That's
the
my
dollar
question.
applies to whatever is on its right-hand side. So the entire expression to the right-hand side of a dollar
Okay.
is the expression. All right, but we are not quite done yet because EAX is the address of the left-hand side. So what is left to do now is we have to evaluate. There are several ways to do this. I will do it this way. I'm going to move I EBP because I is a parameter. So I can do this to EDX. Then I can use another move instruction to move EDX to whatever EAX points to. Because EAX is the address of the left-hand side, EDX is the value of the right-hand side, so I'm moving the right-hand side or copying the right-hand side to the left-hand side in this case. Any questions about this one? Yep.
I don't know why, but for some reason I thought it would be the other way around. You add the left-hand side to the right-hand side. I mean, move.
The way the C code works is you evaluate the right-hand side and you store the value to the left-hand side. But in assembly, we have it the other way around because we have the second operand being the destination. Unless you use the Intel notation.
Which is backwards.
That's a good question too. Just switch one question into Intel notation.
No, that's not good at all.
Look at that.
All right. So any other questions about this one?
I can switch anything to Intel and just make it not work. I mean.
Any other questions about this one? How about the previous one? How about this line here?
Can you show us in a trickier way those bottom two instructions?
No. You gotta get us confused. Seems simple enough.
Okay, how about this one? The implementation of this line, this should be fairly simple. Good? Okay, let's do it. All right, so, we'll go ahead and call, okay. The first part is really easy. You just call default Bst Node. Whatever it returns is going to be in which register? It's going to be EAX. So the next thing we have to do is to deal with the other side. So this time I'll move P node EBP, which is the parameter itself, into EDX. And if I want to write some comments here, I will say EDX points to a
Structure.
oh, this is a structure. Okay, so we can't really quite do it this way. Okay. I forgot about this. Because if you look at default Bst node, it returns an entire structure. So that means we have to use the concept of a return value address, which complicates the whole thing to no end. So this was good. I'm so glad that I actually talked about this one, because this one is the tricky one. There's no non-tricky mode in this case. Okay, the first thing we have to do is to reserve the space for the return value, because it's returning an entire structure. So the first thing we have to do is to reserve that space. But before we reserve that space, well, it depends on how you want to do it. We'll copy ESP to a register, let's say EAX. Because this location is, no, we don't have to do it this way. We have to reserve the space first. So to reserve the space, we have to say Bst Node underscore size, which is the number of bytes that each Bst node is going to take up. We have to subtract this much from ESP. If I want to write some comments here, it will be reserve space for a struct Bst node.
That's because we're returning a struct, right?
Because it is returning an entire structure in this case. Okay?
So for writing this by hand, we should underscore size. That'll be pretty well defined for
Right.
somewhere.
Because I'll give you the assumption that underscore size is the size of operator. Yep. All right. So what we have to do next is to remember the address of this point. So we'll go ahead and move ESP to EAX. So I will write the comment and say EAX points to the reserved struct Bst node as the return value of the subroutine. Is that okay?
Yes.
Because I know that I need that later on. Now I'm ready to push parameters. Do we have any parameters?
No.
Nope. So we do have one thing to push. We have to push EAX, in this case, push return value address. Okay, that's the trick here. And then we call the subroutine. So now we call default. Oh, we have the call already, so we'll just reuse that line. Now it's also tricky, because remember, when we return an entire structure, the return instruction is not just RET, it is RET $4, which means the 4 bytes taken up by EAX here is already deallocated. Right? Okay, so I'll write down here, by compiler convention, the return value address is already deallocated by the callee. It's all in the notes, I'm just doing this as an example. Okay, so at this point, if the return value address itself is deallocated, what is the stack pointer pointing at? What else is on the stack at this point?
Just the address of the first.
Not the address,
The structure.
the entire structure. The return value structure is pointed to by the stack pointer at this point.
What is the structure?
It's a struct Bst
No,
node.
it's just Jeopardy.
Jeopardy.
Answering a question.
For how many dollars?
For an A.
Daily double.
Okay, how's that? Yep.
So just to understand, when it does return, it's going to return the struct node to this place, so we told it to, which is the return val address, right? But then it's going to it's going to catch back up to where it's supposed to be in the program. So kind of confused. How's it going to know to return back to the same? Never mind.
Return to the location. The return location is done by the return address pushed by call itself. The return value address is deallocated because when we do a return, it's returned $4, which means it will not only do a regular return, but it will also decrease the stack pointer by 4 at the same time. So now what do we have to do? What we have here is the stack pointer is pointing to a struct Bst node that is the return value from the subroutine. So when you look at the C code, we have to do something here. We have to copy that return value to whatever P node points to. So that means we have to use mem copy at this point to copy from one portion of the stack to another portion that we don't know whether it is on the stack or not. So the mem copy, okay, I have to use mem copy because I can never remember the ordering of the parameters. Okay, we have to push the number of bytes to copy, the source, and then the destination because we are pushing parameters in a backward order. Push the last parameter first. So we'll go ahead and do this. So the first thing we have to push is the number of bytes to copy. That's the label Bst Node underscore size. Then we have to copy or push the source, which is, okay, where is this exactly located at? Sorry? It gets a little bit tricky at this point because it's still closely related to the stack pointer, but it's not exactly where the stack pointer is. So do you guys want the tricky version or the non-tricky version?
Non-tricky.
Non-tricky,
Whatever's
okay.
simple.
Non-tricky version is to take a snapshot of the stack pointer first, put it into EAX, and then push EAX at this point.
Oh, so we can just add the location.
Yeah, because, well, the reason why we have to take a snapshot is because the push out instruction will change the stack pointer. So I cannot really just say push out ESP at that point because it's already 4 bytes off at that point. But if I take a snapshot of the stack pointer here, then EAX becomes a pointer to the struct Bst node that is the beginning of the return value. All right, we have one more thing to push, which is the destination address. And since we have a cisp instruction set here, we can actually do it with one single instruction, which is P node EBP. Because P node open paren EBP close paren is a pointer to a struct Bst node already. So this means that we have the source, we have the destination, we can now call mem copy. After mem copy returns, those 12 bytes on the stack are no longer useful. So we can deallocate those 12 bytes, and that concludes this one single line of C code.
You know, the problem with something like that is like when you start writing that many lines of code, like in any of the other classes that we have, it's like, oh, I'm so getting this wrong because like you're thinking like, oh, it was simple, it was one line. There should be like 2 or 3 lines. You start, it's like a math problem, you know, your professor gives it and then you start doing 2 or 3 pages and you're like, that has to be wrong. You know
Now,
what I'm saying? You start going wrong, you're like, man, I don't know what I'm thinking of this. There was obviously something very simple.
I know how much you guys here like to understand this mechanism really, really well. So one thing you should do is to implement something like this. It's not a homework assignment, it is just a
Extra credit assignment?
I like this idea.
Yes.
If extra credit.
If
Fun.
Enthusiastic.
is that right? Enthusiastic. That's right. One of the signs of ADD or ADHD is cannot spell, but I can outspell most of my colleagues. That really says something about computer science people.
You can remember where to put
Hey, at least I can spell global. Global is Global, not GLOBL.
In your book, no offense, you did spell it wrong in your book.
Global? Because the assembler will take it both ways.
Oh, really?
Because early programmers using the assembler misspelled it as .global without the A.
Right. All right.
So later on, in order not to cause any backward compatibility issues, they decided we'll just take both of them, the correct one and also the incorrect one. All right. So
You know, spelling is like the least useful skill ever. It's just to mention the spell check on the computer.
Yeah, but you still have to spell your variable names correctly, especially when you use an interpreted language like Perl. in non-strict and no warning mode. Because if you spell something wrong, what happens in Perl? Let's just say that you have been using a local using a variable called lowercase x all along. Okay. Okay. So you use $x, $x in a Perl script, and then one day you say $uppercase x, okay, equals something or refer to it. What happens in Perl if you don't turn on strict mode is the Perl interpreter will say, oh, so you want a new variable called uppercase x and not lowercase x? I'll create one for you right now.
Yeah.
That's the Perl behavior. Which means if you don't get any warnings, you don't get any error message, your program will just get a new variable called uppercase x, not lowercase x. And it will just continue execution until at some point it's going to break. But by that time, it will be like this far away from the actual point of problem. And that's why when you write Perl programs, you always say use strict, so that you have to declare variables before you use them. Same thing in VB. Most interpreted languages have this problem. If you start to use a variable, if it doesn't have it already created, it will create it on the spot at that time. And I cannot remember why I'm talking about Perl. Now that is a sign of ADD or ADHD. Okay, so what we want to do, this is a program that you can write. It's a very simple one. It's easy to debug, but it does confirm whether your understanding of returning a structure is correct or not. So I would definitely do this. Okay, struct v. Okay, simple void. Now this part you want to use some kind of distinct value. Make sure that it cannot be accidental. So I think that's pretty distinct. Return value. And then in another subroutine, you can I'll just call this a stub subroutine because it doesn't really do anything useful. In a stub subroutine, you want to create another local variable v. We'll just call this local variable v. Give it a name x. X gets simple. Printf x dot I equals x dot j equals x dot I, x dot j. And I think this would be just this chunk here. Write this in the main program. You don't need stub. Stub can be your main subroutine. Just give it a return 0 at the end. It's a very simple program. It doesn't have any other logic other than returning a initialized structure. If your program can end up printing 37 and 103, that means you have the right implementation of returning by value a structure. Okay. I think it's beneficial. Okay, I think implementing this program, especially you should implement both parts in assembly. Implement simple itself in assembly, and also implement stub in assembly. Don't do both at the same time. Only do one at a time, because that way you can isolate the problem. Where am I implementing it incorrectly? But this will be very useful. It's a very simple program, as simple as it gets, but it does help you understand the mechanism of returning a value. That is a structure. Okay. Moving on to question number 4, and we are running out of time.
Do it fast.
Now the caffeine is wearing off already. So okay. Find minimum index. Okay, this is one of those programs that I write for cisp310. Okay, any part of this that is particularly difficult to implement. We'll just go ahead and focus on one part. What about this part here, just this line? Is that good? Because it has indexing. Everything else is pretty easy. Is that okay? Okay.
Yeah, that's fine.
So we'll just go ahead and implement this one single line in assembly. All right. We have array indexing here. but we already know that everything is, argv is a pointer to a pointer. So what is this thing here? What is the type of argv square bracket I? By indexing, you are taking away one of the asterisks when it comes to the type. So we still have a pointer to a const char. In other words, it is a pointer. This is a pointer, and so is this. Okay. So how do we do this? Silence.
Well,
okay. How about we do something like this? We know that we need min index, and that's our local variable.
that's right.
Okay, we put it into, say, EAX. And then what are we going to do next? The cisp architecture has a particular addressing mode that makes the next instruction like easy. Now we know we have to push the parameter because this is the second parameter of string compare. So we'll use a push out instruction here. argv is our displacement. EBP is our base register. EAX is our index register. And 4 is our scale.
All right. Let's draw that puppy.
Okay.
That's a snap. Like that.
Actually, I think I'm wrong in this case. argv. Oh, that is wrong. Never mind. This would work if argv is an actual array defined here, but argv is just a pointer to an array, so I can't use this approach. Close, but no cigar. Move argv EBP into another register, say EDX. Now we can do it. Then we can say push L, but this time we have to specify 0 here. EDX, EAX 4, and that will push the first parameter, the second parameter on the stack. Explanation?
Yes.
Okay.
What's wrong with the other one?
The other one is different. The other one is really, really different compared to this one. Okay, let's take a look at this. What is EAX at this point? EAX is min index, which is an index of the square bracket operator. Is that okay? The min index inside the square bracket, it is our index. The second instruction is actually the most important one, or is the easiest one to get wrong, because I got it wrong the first time. Okay, the question is, what is argv? It's a pointer to a pointer, but one way to look at a pointer to a pointer in C is it is an array of pointers. So argv is the address of an array, and each element in the array is a pointer. So by doing this, EDX is the address, is the base address of an array of pointers. Is that okay? Because I'm just copying the parameter argv to EDX. What about the next instruction here? What are we pushing on the stack? What is the operand specifying?
A particular pointer?
Okay, so does anyone still remember the actual address where we are grabbing the content and push it on the stack in this case? The effective address of the content pushed is EDX, the value of EDX, plus 4 times the value of EAX. Because we have a displacement of 0, so that doesn't really get into the equation here. What exactly is that?
That's EDX is the base address, and EAX is min index, but because each thing in
Each
the array
element
is 4 bytes,
right?
you have to multiply EAX by 4, and then
That's
add
the-
it to EDX.
Yep, so that's the address of what we want to push on the stack. but the operand here is going to do the indirect too. In other words, we will go to this location, grab 4 bytes from that location, and push those 4 bytes on the stack, which is what the C code is specifying.
Is that how you translate that? Say that one more time.
Okay. This is the effective address of the operand, which means we are not pushing this on the stack. We are pushing the 4 bytes at that address on the stack,
Yeah.
which is what the C code is specifying. There was another question? Yep.
Can you just explain the logic of how you get to the location?
How I get to the location?
Yeah, okay, like, yeah, just explain EX plus 4 times EAX, like, as far as what's...
Pictures.
Yeah, picture.
We like pictures.
Picture.
Stone and chisel.
So we know that ARGV is one of the parameters. Okay, it's pushed on the stack. And we have some gibberish here that's also on the stack. One of the gibberish here is min gibberish, yes. So one of the gibberish is min index itself. Okay, is that okay? Now min index is an integer. It starts with 1. So we know it's kind of like a 1, 2, 3, 4. It has consecutive values like that. ARGV on the other hand is a pointer. It's an array of pointers. So what you can do is to look at this as a pointer to an array. Okay, each item is a pointer to a string. It's basically a string. It's a pointer to a char. Okay, that's 4 bytes. Are we doing okay so far with this picture? Okay. So now we look at the first instruction. This part is pretty easy. EAX now has the same value, which is 1, 2, 3, 4, and so on. We look at the second instruction. ARGV is copied to EDX. So that means EDX will also point to exactly the same place. Are we still doing okay so far? Okay. The effective address of this operand is EDX, which is pointing to the base of the entire array, plus EAX times 4. So EAX times 4, if EAX is 0, then they will be at the same place. If EAX is 1, it will be this one. If EAX is 2, it will be here, and so on. But that's the address. The operand is specifying not the address of EDX plus 4 times EAX. It is specifying the content. In other words, if EAX has a value of 2, then we'll be pushing whatever is at this location on the stack. Is that making any sense? But what exactly is at that location? It's an address to a char, which is also known as a string in C. And that's what the C code is doing, is pushing a string on the stack. Because string compare, guess what? Compares strings. Is that making any sense? Okay. Are we doing okay so far with this?
So that's where the second dereference comes in, is in the push L instruction,
because we are not pushing the address of this
Right,
element.
it's
We are
the
pushing
content.
that element on the stack.
Yeah.
Yep.
Okay.
Okay. So that's the second argument. Okay. Are we ready for the tricky version to push the first parameter?
Yes.
You guys are always ready for that.
Sleep aids might do.
Yeah, call them Mountain Dew girls.
There we go.
Mountain Dew girls need extra diet.
Good enough.
Doesn't matter.
It doesn't matter.
It doesn't matter. All right, so here we want to implement the first one, but we don't want to use the same method. We want to use a quote-unquote tricky method to do it. Okay, so the tricky method is to move EBP, which is a local variable, into, say, EAX. And then we do our usual, trick here. Do it twice, then we have 4 times of that value. Right?
What?
That's not the short way.
And then we add the base address of the array of pointers to EAX. And then we push, well, we'll do it one more time since we're so risky today. So we'll go ahead and risky, as in R-I-C-Y or R-I-C-K-Y. R-I-S-C-K-Y. Risky. That should do the same thing.
And then you call.
Yeah. Then you call string compare.
And then you call, okay, since we're here, might as well just do the whole thing, right? We call string compare, and then when string compare returns, we have to adjust the stack pointer to balance the stack. Oops. After we balance the stack, we'll compare that to 0. So CMP L $0 to EAX, because the return value is in EAX. And we want to branch around the conditional statement. So we'll have to say jump if it is not less than 0. So jump if greater than or equal to. So jump if not less than, to a label end if. And I would just put the end if label here. That's actually a valid C code, so I can just put it that way. Is that okay?
Yep.
So, it's all good? Now, once again, I want to use different implementations of the same code, because if I use the same thing over and over again, we're not learning anything new. It's just copy, paste, and then change one of the reference. But you have to understand why the alternative also works in this case. It really accomplishes exactly the same thing, except we're using different instructions to accomplish that. Are we doing okay so far? I would look at the second implementation, since I did not have time to comment it. You might want to put some comments next to this code. Someone can send me a note to remind me to upload this code. It's already saved on my thumb drive.
I already emailed you.
Brandon probably has an email sent before the class. Please remember to upload the video and the file. Or have it as a cron job. Every Tuesday and every Thursday, send that via email by 8:30 p.m.
Let's write that part.
All right. So we are still missing 2 questions. I can try to do that tonight, and I'll send you the vid. Unfortunately, that means there won't be a whole lot of interaction. But I think we covered all the tricky cases, all the kind of really tricky questions. Yep.
Were you supposed to answer the other?
That's what I said. I will do it. In a video that I captured either tonight or tomorrow night, because tonight I might have to do some really important work.
Two questions.
One, we don't have class.
Now everything